I'm going to show you the basics of fine-tuning on multiple GPUs. I'll show you a few methods: naive model parallel, distributed data parallel, and fully sharded data parallel. These methods will allow you to improve the speed of your training if it's a small model, or if it's a large model that doesn't fit on a single GPU. And sorry about the eye, I took a bit of a tumble over the weekend, but should be healed up soon. And for agenda. First up, we'll discuss what kind of multi-GPU training you should do based on your model and what you're trying to achieve. In particular, I want to talk about VRAM requirements, how you calculate the VRAM requirements for a model of a given size, and also for a data type, for example, 16 or 4-bit training. Then I'll talk about the three main types of model training that I described in the intro, and I'll show you the code modifications necessary on a very simple training script if you want to do each of them. Then last, I'll show a few results of some training I did on Tiny Llama, which is a small model in distributed data parallel compared with model parallel. And I'll also show you the results of Code Llama, which is a larger 34B model. And I'll show you that training in fully sharded data parallel versus in model parallel. So there are three questions to look at when deciding on what kind of GPU training to do. The first is what your model size is. The second is what accuracy you want, or what perplexity you want out of the fine-tuning. And then the last is whether you're trying to optimize for speed, so you want to get the training done quickly, or you want to minimize the number of GPUs or your cost for training. And all of these aspects are going to feed in first to the VRAM requirements. And once you have the VRAM requirements based on your priority, that's going to inform what kind of GPU setup you want, whether it's model parallel, data parallel, or fully sharded data parallel. So I'm going to spend a bit of time talking about VRAM requirements, particularly how it relates to the requirements for the model parameters, the gradient parameters, and the optimizer parameters. In all of this, just keep in mind that 8 bits is equal to 1 byte. So anytime we're representing a number and we want to represent it in 16 bits, that's going to correspond to 2 bytes of VRAM that we need for storage. Moving to VRAM requirements for training any model, there are a few buckets that take up the VRAM or virtual RAM. There are, first of all, the model parameters. So if you have a 7 billion parameter model, you need space for those 7 billion parameters on the GPU. But you also need space for the gradients, you need space for the optimizer states, and you also need space for the activations. And I'm going to describe this all in a little more detail. So let's consider a toy model, a model that just has 3 layers here. And let's consider these are simple linear layers, and there's just one weight per layer. So I've weight 1, weight 2, and weight 3. And the inputs are going to come into this model, and the input will be multiplied by the first weight. So weight times input equals the output or the activation. Then that will be multiplied by the second weight to give the second activation, and multiplied by the third weight to give the third activation. And this third activation here in this toy model is going to be the final output of the model, and that will allow us to compute our loss. And the loss is going to be the output, or the last activation, minus some reference value for what the final value should be if the model was perfectly trained. So here's this very simple model with 3 weights. There'll be 3 activations coming out, and there's a loss, and that loss can be used then to back propagate and update each of these 3 weights. So let's look at the back propagation. So we've taken the input, multiplied through, calculated the loss, and with the benefit of this loss, we're going to work backwards now in the back propagation stage. So we'll take the loss, and considering the activation 3, we're going to calculate gradient 3. And then using the chain rule, which I'm not going to describe in detail, but basically by taking gradient 3 and activation 2, we're going to be able to calculate gradient 2. Then taking activation 1, we'll be able to calculate gradient 1. So all I'm showing here is forward propagation in a simple model, calculating the activations, getting the loss, and then back propagating to get these gradients here. Now, since this is a very simple model, I can show a representation of the optimization here on a 2D graph. So on the x-axis, I've got the value of the weight. We can just consider weight number 1 for now. Let's say we're optimizing weight number 1. And here I've got the gradient, G1. So this would be the gradient that is calculated during backpropagation. And on the y-axis, I have the loss, which is what we're trying to minimize. So this is a graph of how the loss varies if we change the value of this weight, in this case, the first weight. And this dashed line here represents the loss. Of course, we don't know this in advance, but I'm just saying, let's imagine that we're optimizing something that has an optimization shape that's roughly like this. So here we have the weight and we have the gradient. And now we're going to optimize, which means we want to take a step towards the very bottom of this loss function here. So in the toy optimizer, if we take the simplest approach, which is stochastic gradient descent, we might come up with a way to optimize where the new value of the weight, so we want to shift this weight to the right, is just going to be the old value plus some delta times the gradient, which I should have in a different color here. So very simple optimizer for the toy model. We just update the weight to take a step in the direction of this gradient. And that's a really basic way of how a language model, or indeed a neural network in general, can work for backpropagation. You forward propagate, you calculate the loss, you get the gradients using the chain rule, and then these gradients are what allow you to take a step with the optimizer towards the local minimum. And the most basic approach is SGD, which is stochastic gradient descent. Now, the reason I'm showing you this is so that you can appreciate when we are storing weights in the VRAM, we also need to store the value of these gradients. So that's important because it tells us, again, something about what needs to be stored. You'll remember earlier on, I said we need to store the model parameters. And now I'm showing you that we need to also store the gradients because these are used in order to do the optimization. Now, in this very simple type of optimization, there's actually nothing else that needs to be stored, just the model parameters and the gradients are sufficient because you can see in our simple formula here, when we update the weight, all we need to know is the previous weight and the gradient, and delta is some tunable constant. But we don't need to know any other information about the optimizer because it's such a simple optimization approach. Now, the problem with using this kind of a simple standard gradient descent is that it's just not particularly stable during optimization. For example, if you have a loss function that's kind of bumpy like this, one of the problems is you might get stuck at the bottom of one of these little valleys, and so you're not able to move down to the global minimum. And so one of the approaches for getting around this is, instead of just considering the gradient at this specific point where we want to take a step forward, we can consider some of the historical gradients and we can average those. And by averaging the historical gradients, some of which are pointing down, but actually this one here would be pointing up because of that local bumpiness. By taking this average, we're still going to have something that kind of roughly points down and should move us along these bumps towards the global minimum. So using a historical average is one kind of improvement we can make upon the standard gradient descent. Now, there are some other problems with just a stochastic gradient descent approach. One is that if you have gradients that vary from being very small to very large, so suddenly you have a large gradient, the optimizer might decide to take a very large and crazy step. Or conversely, if you have gradients that are very smooth and small and there's not much variance, you may not move very much along a plateau. So it might take a very long time to reach the bottom of this curve here. So it would be really nice if we could amplify the small gradients to keep moving when we're in these flat troughs and then dampen the large ones when there's a sudden change to a large gradient. And the way that this can be done is by considering not just the history of the gradients, but the square of the gradients or their variance. So if you look at some kind of accumulated variance, it's going to be a combination of some small amount of the latest gradient squared plus some larger amount weighting of the historical gradients here, gradient squared. And what we can do if we have this kind of a weighted historical variance is if we have a big value, we can then dampen the step that we want to make. And if we have small variance, then we can accelerate. And basically, this is what the Atom optimizer does. It takes these two ideas. The first is that it averages the gradients so that you have this momentum and you can power through choppiness. And second of all, it will use the variance in the gradients in order to dampen or amplify its movement so that you can keep moving in troughs, or you can slow down if there are big choppy changes. Now, if you want to dig in deeper, you can always chat with GPT. Here you can see in mathematical form. I'll just increase my screen a little bit. Here we have an equation for what's called the momentum term. It's basically the averaging of the gradients. So here I have the gradient at time t, and it's being added up with the previous gradients. And likewise here I have the gradient squared. So this is my variance term. So v here, which is called the adaptive term, is used in order to adapt if there's high or low variance. And the way that this adaptive term is used to actually adapt is whatever the momentum term is, which is m. You can think of that m as the average gradients. You ultimately divide that value of m by a square root of the adaptive term. So if the adaptive term is high, if there's high variance in the gradients, that means it's going to reduce the size of the overall update. And if there's low variance in the gradients, then that's going to increase the rate at which we're going to take a step forward in future. And so this here is the atom optimizer. And you're wondering, well, why did Ronan tell me all of this? And the reason is because it all links back to VRAM. So because we use this more complicated optimizer, we need to store now the model parameters. We need to store the gradients because they're needed for update. And we also need to store the gradient history for the momentum term. And we also need to store the gradient variance history for the adaptive term. So what this means in terms of VRAM requirements is that we need to store 4 different things. And this significantly increases the amount of VRAM that you need for training. So just to look in detail now, every parameter, if it's a 16-bit parameter, is 2 bytes. Every gradient, if it's 16-bit, is 2 bytes. But we need to add on these momentum terms and the adaptive terms. And what's even worse is that generally for the optimizer to be stable, it's not enough to use 16-bit numbers. It's common to use 32-bit numbers. So the momentum term is actually a 32-bit number, which is 4 bytes, the same with the adaptive term. And furthermore, because the optimizer needs to use the parameters, there needs to be some form of those parameters stored in 32 bits as well. So even if we have the model being trained in 16 bits, we still need to store a copy of those parameters in 32 bits. So you can see that a lot of the VRAM requirements is linked to the way that we're doing the optimization. If we did standard gradient descent, we would need a lot less storage in VRAM, but that's just not stable. So we use the atom optimizer. And so if we sum up the number of bytes, we have 2 for parameters, 2 for gradients, 4, 4, and 4. And that leads to needing about 16 bytes for every parameter of the model. So if I have a tiny llama, which is about 1 billion parameters, that means I need a minimum of 16 gigabytes or billion bytes if I'm going to fine tune llama. And if I want to fine tune something like llama 70B, then that's going to be 70 times 16. So 76 is 42, 717, and 4. So over 1,000 gigabytes in order to fine tune llama 70B if you want to use all of these states here. Now there's one other set of parameters that will contribute to the VRAM requirements, and that's the activations. And the activations are stored because on the forward pass, you're calculating the output of each layer, and those activations are needed then to calculate the gradients when you come back. So on the way out in the forward pass, you're calculating these activations, and the activations are each the product of the weight times the input. And of course, the number of inputs depends on the batch size, but also the sequence length. So if you send in a very large batch of 32 rows of data, and they're all very long, that means there are a lot of inputs and a lot of activations, and all of those activations have to be stored because they're going to be needed in calculating the gradients when we go backwards on backward pass. And so the more of a batch size, the larger the batch size you use and the larger the context length, the more VRAM you'll need when you're doing the training. And so this leads us to a basic principle for GPU setup. Your GPUs are going to need to fit the model, they're going to need to fit the gradients and the optimizer, and at a very minimum, they're going to need to fit one batch. So as a baseline, if you start with enough GPUs to fit the model gradients and optimizer and see then if it will run with one batch, you can from there increase the number of batches and see if it runs out of memory as you increase the batch size. So all of this was to give you the highest level explanation of the amount of VRAM we need if we're going to fine-tune a model in 16 bits. Now, depending on the accuracy you want for fine-tuning, you're able to reduce the memory requirements significantly. The first way is using LoRa, and the second then is using quantisation. And I'll go through how each of those affects VRAM. The most basic way to reduce VRAM is to quantize. Quantization means representing numbers using fewer number of bits, which is less precise. For example, you can represent each number with 4 bits instead of 16. And what this does is it will reduce the total number of bytes per parameter down to 0.5 instead of 2. So for a 16-bit number, you need 2 bytes. There's 8 bits per byte. For a 4-bit number, you just need 0.5. Now, unfortunately, you can't easily quantize a lot of the gradients and the optimizer terms because if you quantize them too heavily, you'll just lose stability and the trading is not going to converge. So just doing quantization on its own actually doesn't reduce the amount of memory or VRAM that you require by all that much. There's a much more significant reduction if you use a technique called LoRa. The idea with LoRa is for all of the parameters in your model, so these parameters here, you're just going to take the weights in the matrices representing those parameters and freeze them. So let's just consider one matrix that's 1000 by 1000. And instead of training this matrix of roughly 1000 by 1000, we're instead going to train 2 smaller adapters. And these 2 adapters will have the same width, about 1000, but they'll have a much smaller height or rank. So the rank here is 8. And you can see I have 2 1000 by 8 matrices here. And the idea with LoRa is to train these 2 matrices, which when multiplied together, so if you multiply these 2 matrices, they'll generate a matrix of this size, 1000 by 1000. So if we train these 2 smaller matrices, we can multiply them and then take that product and superimpose it on top of this frozen weight matrix here. And what this allows us to do is to fine-tune a much smaller number of parameters than we would be doing if we were doing a full fine-tuning on the base model. And I'll just show you here how much of a reduction this gives. So, for example, if we train 2 8 by 1000 matrices instead of a single 1000 by 1000, we've got 1/64 times the number of parameters to train, which is a very significant reduction. And this is even more significant because if we freeze the base parameters, that means we don't need to store gradients or optimizer terms for all those parameters either. So actually by using LoRa, we're greatly reducing the number of gradients we need to store by a factor of 1/64. The same with the momentum term, the same with the adapter term, and the same with the parameters we need to store in 32 bits for the optimizer. So basically, LoRa is extremely significant for reducing VRAM requirements because it more or less just takes out the VRAM requirements. I mean, it's really small for these gradients and optimizer requirements and leaves you primarily with the memory that's required to load the base model. Even though it's frozen, it needs to be available in VRAM for doing the calculations and then the activations. So LoRa provides a very, very big reduction in the VRAM that's required for fine-tuning. Now, once you've done LoRa, the reduction in VRAM that comes with quantization becomes a lot more significant. So here you've got 2 bytes just for the parameters if you're using LoRa, assuming that everything else has become very small. And now if you quantize with 4-bit quantization, you're able to reduce from 2 bytes down to 0.5 bytes. And that's why doing QLoRa or quantized LoRa allows you to get really low overall VRAM requirements. So I hope you can see why full fine-tuning is extremely intensive in terms of VRAM. It's because you've got these gradient and optimizer states. LoRa really reduces that down close to 0, not 0, but much, much less. And then with quantized LoRa, you can reduce the VRAM required for the parameters themselves. Now, of course, this isn't a completely free lunch. If you're using LoRa, that will reduce a little bit the quality of the fine tuning. It's not quite as granular as full fine tuning, although there are techniques now like rescaled LoRa and potentially even DORA that allow you to get much closer to full fine tuning. And then if you move further and do the quantization, that will also affect the quality a little bit. So again, not a free lunch. And that's why I asked the question, what accuracy do you want? If this is pre-training a model, then you're probably going to want to do full fine tuning. In many fine tunings, I find that doing LoRa but not quantized is a good approach. It can get very good performance. And if you really are tight on VRAM or you want to minimize cost, absolutely, then going for the quantized approach is going to lead to the lowest amount of VRAM. Okay, so now we understand the VRAM requirements based on the model size and based on the quantization or approach of using LoRa or not. So the next question we finally get to is, what kind of GPU setup do we want? And this is primarily going to depend on whether you want to minimize the number of GPUs or cost, or whether you want to maximize training speed and you're willing to pay for more GPUs. And there are a few configurations that we can use, a few ways to spread the VRAM across multiple GPUs, and that's what I'm going to talk about next. In terms of GPU setup, the most basic approach is to do something called model parallel. Of course, if everything fits on one GPU, there's no parallel, it's just model, I suppose. But this is always the starting point, and I'll explain how with one model, you can just take the top layers and move them to another GPU if all the layers don't fit on the first GPU. So there's this question of whether your model is going to fit on a single GPU. If it fits on a single GPU, then you can use a technique called distributed data parallel to get more speed, which basically replicates the whole model onto multiple GPUs, so you can feed data in parallel to each of those. And the other approach, if your model doesn't fit in one GPU, is that you can start to shard the model. This is a little bit more complicated, but it involves taking one layer and splitting it into pieces across the GPUs. So every layer is going to be split somewhat horizontally across GPUs. And now when this first GPU wants to do forward propagation through the first layer, it will call the information about that layer from the other GPUs, assemble it just for that layer, run forward propagation, and then it's going to move to the next layer where it will call information for that next layer, assemble it, and run forward propagation. And I'll show you that a bit with diagrams. Again, we'll use the toy model here. So we're feeding in an input, calculating activations on the forward pass, calculating a loss up here based on what the reference values should be, and then back propagating to calculate the gradients. And given the gradients, then we're going to use and update the optimizer states because we're going to use Atom as an optimizer. And that's going to allow us then to update the weights in our model. So this is the high level process. I'm just showing it here because I want to highlight I'll be talking about weights, gradients, and optimizer states. So in the simplest case, everything fits onto one GPU. So our toy model here with 3 layers, the weights, the gradients, and the optimizer states, and the activations, by the way, all fit within a single GPU. We feed in a batch, we do forward pass, and we do backward pass. So this is the simplest case. The model just fits. And because it fits, that allows us to parallelize quite easily just by making replicas. So this is called data parallel. It's where you add more GPUs and you basically replicate the whole model and you feed in batch number 1 here, and in parallel you feed batch number 2 into the replica. And at the end of each batch, you have this communication between the GPUs, and the gradients are communicated so that everything can be realigned after the batch, and that basically allows for parallel processing. You then move on and run 2 more parallel batches here if you have parallel GPUs. So the data parallel approach here is quite straightforward if you have a model that's going to fit fully on a GPU. And there are various optimizations around how the information is communicated efficiently between the GPUs. One efficient approach is called distributed data parallel, and I've just linked here the PyTorch implementation. It's the implementation I'll be showing later on with the examples. Now the next case is where the model doesn't fit on a single GPU. For example, maybe the first 2 layers fit, but the third layer here of weights doesn't fit on GPU 0. And the naive approach here is just to tack on another GPU above it that will cater for the third layer here. And you can keep tacking on GPUs. So if you had very many layers, you would be able to just put the next layers onto a next GPU. And here what happens is you forward propagate through layer 1 and layer 2. GPU 1 will just be chilling, not doing anything. And then when you've gone forward through the second layer, you'll pass the activations on to the next GPU and you'll run layer 3. Then you calculate the loss and then you'll start to back propagate in GPU 1. And so you'll back propagate to get gradient 3. And then you're going to take that information and pass the gradient info down to GPU 0. And then you'll start to back propagate through layers 2 and finally layer 1. So this approach here is quite simple and it works very well. In fact, I wouldn't underestimate it as an approach because the simplicity means that it often will run a lot more reliably than some of the more complicated approaches I'm going to show, like fully sharded. But the drawback, if you just do this naive model parallel, is that you typically have only about one GPU active at a time. So when the first one is working on forward pass, the second one is chilling. And when the second one is working, the first one is chilling. And this results in bad utilization. You're just not using the flops, the floating point operations of the GPUs to the maximum extent, which means you're not maximizing or minimizing rather the total training time. So the solution to this is called fully sharded data parallel. It's fully sharded because you shard not just the weights, but the gradients and the optimizers. And it involves taking each of these. So for example, taking weight number 1 and splitting it into 2 parts. So if you think of a matrix, you're just going to split the matrix in 2 and you're going to put part 0 on GPU 0 and put part 1 on GPU 1. So here, there's not a complete copy of the model, gradients or optimizer. On GPU 0, it's actually half. And on GPU 1, it's also half. Now, you're wondering, well, if I feed in a batch, how am I actually able to process that batch? Because I need all of the weights to process a batch in the forward pass. And the answer is, on the fly, I'm going to take in the information from part 1 of the weights and combine it with part 0 of the weights so that I have the full weights here on GPU 0. So on the fly, I grab this information, run my forward pass, calculate the activations. Then I'm going to, on the fly, pull in information from GPU 1 over here so I can make up my full weights just as needed in GPU 0. And then the same with the third layer. So basically on the fly, I pull in the weight information, move to the next layer, move to the next layer. I get to the top, calculate the loss. I'm ready for back propagation. And in back propagation, I'm going to work downwards on a layer by layer basis. I'm going to update these weights with the help of the optimizer state that's associated with these weights. And in order to do that, I'm going to need to get gradient information from the other GPUs. So on the back propagation step, I'm pulling in gradient information from the other GPUs. And actually, once I finish one layer of back propagation, I then distribute back out the gradients so they're stored in pieces across the different GPUs, and that's called a scatter operation. So after I've got the loss, I back propagate, mixing the information, well, gathering it in and scattering it back out, and work downwards to back propagate and update the weights that are within my GPU. Now this happens in parallel at the very same time in each GPU. So for example, in GPU 1, it's on the fly gathering information in so that it has enough of the weights, or it has all of the weights in the first layer and can do a forward prop step. Then it will on the fly gather layer 2, then layer 3, then it will back prop, do the gradient communication, and it will continue with the back propagation to update all of the weights in this shard of the weights on GPU 1. So this is how fully sharded data parallel works. And the difference between the approaches is quite simply that if you can fit all of the weights onto a single GPU, then you can just kind of make replicas. Whereas if you cannot fit on one GPU, you're going to have to shard the weights, the optimizers, and the gradients across the GPUs and assemble them on the fly to do partial computations forward and backwards. So there's not a free lunch here either. In a model parallel setup, you have very low communication overhead. You don't have to do anything on the fly. There's very little information being passed between GPUs. It's just at the interface when you move from one layer to another. Whereas when you are in the replica approach or distributed data parallel, you need to communicate a lot of information on gradients because you need to synchronize the gradients after batches have been run in parallel. And in the fully sharded data parallel approach, you've got a lot of communication overhead because you need to assemble weights on the fly. And then in the backprop, you need to do this communication of gradients to get the info and rescatter it back out again. So back to our original question of how do you set up the GPUs? Well, you can always do model parallel, but after that, if you want to improve speed, you ask the question, does my model fit on a single GPU? If it does, then you can get more speed by doing distributed data parallel and making replicas. Or if your model doesn't fit on a single GPU, you can get more speed by doing fully sharded data parallel and adding more GPUs that each will hold a shard. And for the rest of this video, I'm going to show you the code changes you need to make if you want to do distributed data parallel using PyTorch and the help of Hugging Face's Accelerate library. And I'll also show you how to use fully sharded data parallel. That's another PyTorch library, but I'll implement it using Hugging Face's Accelerate as well. Just a note that although there are pure PyTorch libraries available here for each of the approaches, there is also a library called DeepSpeed, which is a development of Microsoft. It's basically an extension of PyTorch, but it does things a little differently than the PyTorch implementations. And it also has different naming. So here's the explanation of naming. It's easiest to start by thinking about DeepSpeed Stage 3, which is equivalent to PyTorch fully sharded data parallel. It involves sharding the weights, the gradients, and the optimizers. So basically DeepSpeed Stage 3 is equivalent in effect. It's not exactly equivalent in construction or code, but it has the same goals and the rough high-level approach of fully sharded data parallel. DeepSpeed Stage 2 involves only sharding the gradients and the optimizer. So this is in a case where you're maybe doing a full fine-tuning. You can't fit the gradients and optimizers and model weights on a GPU, so you want to shard those. Stage 2 won't work though. If your model weights are too big for a single GPU, you need to shard the model weights themselves, so you need to use Stage 3. And then there's Stage 1 as well, where you just shard the optimizer. So if you have a model that fits on a GPU and the gradients fit on the GPU, but the optimizer makes it too big, you could just shard the optimizer and do DeepSpeed Stage 1. In practice, for what I do, I find that either I'm going to use this here, Stage 3, or not, and that's because I use LoRA. So really, typically the optimizer and gradient parameters, the number of parameters is very small when using LoRA. So really all of the sharding needs to take care of is primarily to reduce the amount of weights that are needed on a given GPU. So typically if I'm going to train a model that's larger than a GPU, I'll use PyTorch fully sharded data parallel. But what I'm saying to you now is you could alternatively use DeepSpeed Stage 3. Now, just a final note here. I know this is a lot of layers, but the way that the libraries are implemented, you could directly try and do PyTorch fully sharded data parallel. That's perfectly possible, and I've linked it on an earlier slide. But you can also use a wrapper called Accelerate from Hugging Face. Accelerate wraps around PyTorch, DDP and FSDP. It also wraps around DeepSpeed, and it's basically a configurator. So you can run the command accelerate config, and it will ask you a series of questions, and it will then set up a configuration file that allows you to run either these direct PyTorch libraries, or it'll allow you to run DeepSpeed itself. So that's what I'm going to do and walk you through. Now, I'm going to show you some of the results just to give you a sense of speedups, and I'll walk you through as well how I set up the code for this. But I ran a tiny llama model, which is a very small model that easily fits on pretty much any GPU. And I fine-tuned it with LoRA using 4 A6000s, which each have 48 gigabytes. You can see here some of the setup around batch size 16 and gradient accumulation of 2. And as you can see, when I run in model parallel, which is not particularly parallel because the tiny llama model fits on a GPU fully by itself. But if you feed in the data only to one GPU at a time, you're going to have bad utilization. As you can see here, it matches roughly the 1/4 GPUs and a training time of about 4 minutes. Whereas if I run in distributed data parallel, I have nearly full GPU utilization and my training time is just about a minute. So that's the speed up there. I can get by using the same number of GPUs, but switching to distributed data parallel. And the second example is running CodeLlama, which is a 34B model. I'm running it using LoRA, so most of the VRAM I need is for the model weights. So if I'm training in 16 bits, that's 2 bytes per 16-bit number. So roughly going to be 70 gigabytes that I need at a very minimum. But I've made it very safe by taking 4 A6000s. So I've almost 200 gigabytes of VRAM here. And again, I've trained using model parallel, which will just take some of the layers and pass it off to another GPU, and using fully sharded data parallel. And you can see here my utilization in model parallel is about 20%, took me 47 minutes. And in fully sharded data parallel, my utilization is almost 100%, and it took me just 30 minutes. Now you can see here the speed up I get. It's not a 4x speed up. Even though I use 4 in both cases, I don't get a pure 4x speed up because there's quite a lot of overhead, as I described with the fully sharded data parallel approach, because all of the weights need to be gathered on the fly, and there's a lot of communication as well around gradients during the back propagation step. But still, you can see that there are significant speed ups by moving to the sharded approach versus the model parallel approach, which has very poor GPU utilization. For the code examples, I'll be working out of the advanced fine-tuning repository. This has many branches allowing you to do all sorts of fine-tuning for memorization, DPO, chat fine-tuning, function calling, long context, quantisation. But now it has an extra branch for multi-GPU fine-tuning, including distributed data parallel or fully sharded data parallel. And it supports supervised fine-tuning and also preference optimization using ORPO. So I'm going to head over to the branch now for multi-GPU. You can purchase lifetime access to this repository, but I'll make sure to give you enough info with the code snippets today. I'll describe it in enough info that you should be able to replicate any of this by yourself. So within the multi-GPU branch, there are a set of scripts that allow you to run very quickly tests on model parallel, then on distributed data parallel, and also on fully sharded data parallel. Then back within the main branch, or rather the multi-GPU branch, we have right here a train and test script. This allows you to run a set of test data to generate the completions for a set of prompts. And the training script, which I'll go through a little bit later, allows you to run either supervised fine-tuning or preference fine-tuning on a model using fully sharded data parallel or distributed data parallel. Now, usually in my videos, I use Jupyter notebooks, and I'll start an instance on Runpod, upload the notebook and get to work there. But when you're working with multiple GPUs, it's actually easier to run scripts from the command line, which is why I have these all as .py files and not as IPYNB files. Now, if I'm going to be running scripts on Runpod, it's actually easier to SSH into Runpod and then git clone the repository rather than having to manually upload the files, which can be a bit more cumbersome. So if you want to do that, when you've signed up to Runpod, or if you have an account, you'll need to set up an SSH connection. This can be done in your settings, and you can find full instructions from Runpod on how to do that. You'll want to head over to your profile. You'll want to head to runpod.io, console user settings, and then underneath API keys, or rather SSH public keys, what you can do is set up an SSH key in your .ssh folder on your computer, and you'll want to then take the public key, the public part of the public-private key pair, and input it here into your SSH public keys. So I'm going to get started now and set up a pod. I'm going to choose to use the Trellis fine-tuning template. So I'll click here on deploy GPU, and I'm now going to look for an A6000. So here we have an A6000, and I'm going to run that with 4 GPUs. So here I'm going to run that on demand. And next I'm not going to need the Jupyter Notebook because I'm going to have the SSH terminal access. Now, while I'm waiting for that to load, I'm going to go over to VS Code. I'm going to click here and I'm going to click on connect to host. And now I want to configure my SSH hosts. And you'll see down here, I've got a host for Runpod. I actually have 2 because sometimes I run 2 pods. And I need to update this information so that it matches what I have on Runpod. So here, now that we're running, I'll go to connect and I'll grab here this address, and I'm going to copy it in right here. And then I'm going to grab the port, copy it here. And this is the ID for the public-private key pair that I've created on my laptop. So everything now should be ready. If I save that file, I can go down here and connect to host. And I'm going to connect to Runpod. And now it should ask me if I'm okay connecting. So I'll click continue. And now I'm connected. So next I want to clone a repository. So I've just clicked on the files, clone repository, clone from GitHub. And I'm going to put in the repo name. Now this repository here, it's a private repository. I'm logged in with GitHub to VS Code. So I'm able to click on this private repo. And that should just clone it into my files. But I need to choose where exactly. And what I want to do is click on the 2 dots so that I can spot workspace. I'm now within the GPU, rather I'm within the instance. And I'm just going to clone there within workspace. And it's now going to ask me if I want to open up the folder. So I'm going to choose to open that. And you can see I've opened up that folder, the advanced fine-tuning repo. And you can see down in my terminal that Runpod is running. So next I'm going to switch into the multi-GPU branch. So sorry you can't see that there, but I've just done git switch multi-GPU, and now all of the files in that branch are open up. And next I'm going to take a look at the test scripts here, but first I do need to do a little bit of installation. So I'm going to go to the README file and I'm going to check out the installation instructions. So I've already switched to the multi-GPU branch, and next I'm going to want to do some installations. First, as part of these installations, you'll see I'm setting up a virtual environment called TrellisEnv. Then I'm activating the virtual environment, upgrading pip. Then I'm installing the requirements. Then I'm installing Flash Attention. Then I'm enabling Hugging Face Hub transfer. This uses HF transfer, which can download weights extremely fast. And then I'm going to log into Hugging Face so that I can push and pull from Hugging Face repositories. Now, just a few quick notes on the requirements. So these are the packages being installed. You'll see datasets, SciPy, Hugging Face transfer for quick transfer of weights, Hugging Face Hub so I can load weights and push to Hub, weights and biases for tracking. I install Wheel, which is helpful for installing Flash Attention. And then I install from source, these are the dev versions, Transformers, Accelerate, Parameter Efficient Fine-Tuning, and TRL. That's for training. And then I install DeepSpeed, INOPS. Actually, I've got weights and biases listed twice, which is a mistake. And then I have Sentence Piece, which is needed if you're using the Yi tokenizer, for example, in some other models. And then I've NLTK and Xformers here as well. Now, just while we're waiting, if you are SSHing in and you want to push to GitHub, you do need to first provide your email and your login. So there's a little snippet here that you can grab from. I'll just scroll down if I search for GitHub. So you need to put in your username and user email using git config. And you can actually get an email that will remain private from GitHub if you go to your settings. So that's a small tip. So the installations are done now, and I'm going to paste in my Hugging Face Hub token. And that should allow me to log in. And now I'll be able to push and pull from the repo. So first thing I'm going to do is explain a basic script for doing some fine tuning. And then I'm going to explain what changes to make to do distributed data parallel and to do fully sharded data parallel. So the very first thing I'm going to do is set up a data set. So I'm using the Tim Detmer's Open Assistant Guanaco. And I'm going to just work with the tiny llama model, which is just a 1.1b model. It'll allow me to quickly do things. So here I'm loading the tokenizer. Optionally could use quantisation. In fact, I've got it set up right now. Then I'm going to load the model with quantization, as I mentioned. And then I'm going to apply LoRA. I'm not going to do full fine tuning because that would require a lot of GPUs for the gradients and optimizers. So here I'm setting up LoRA. I'm targeting these modules. Now, in order to get much better quality fine tuning, sometimes you can add in modules that are not LoRA, so you can make the embedding and norm layers trainable. I talk about this for chat fine tuning and long context fine tuning. It's necessary to fine tune the embedding and norm layers. So this is where that can be set in a very compact and efficient way. Now, this will greatly increase the number of parameters. So instead of having 100% of the parameters being fine tuned, it's more like a few percent, maybe 10% compared to just 1% if you're doing LoRA on its own. So this will add significantly to VRAM requirements if you choose to train the norms and embedding layers. Next, I'm going to set up some of the training parameters. So just use a short sequence length, batch size of 8, 2 gradient accumulation steps, setting up some of the other trainer parameters and feeding them in to the training arguments here. Then I'm just going to instantiate the trainer using the dataset that I initiated. I'm going to be using data in the text column of that dataset, which is actually the only column of that dataset. And then I'm going to call the trainer and train. So to run this, I'm going to run Python and test pp.py. Let's see how that goes. Now it's called PP for pipeline parallel. That's kind of another term for model parallel. Technically in pipeline parallel with multiple GPUs, there are ways to make overlapping some of the processes. So maybe I should have just called it model parallel. So you can see the model is being downloaded here. It's about 4 gigabytes in size because it's actually stored in 32 bits, not 16. But that's downloading extremely fast, so should be done soon. And then the shards will be loaded onto the GPUs, and then training will commence. Now you'll see that in this script, I'm just training for a very short number of rows. Let's see here. I've got the max steps. So max steps is set, and it looks like maximum steps I have is just 1. So a really short training. I'm being asked for my weights and biases. So I'll say use an existing account, and I'll paste in my API key. And now the training has proceeded, and you can see 1 step of training is complete. And now the logs are available if I want to check them out at weights and biases. So that's the very first run through, and that's using model parallel or naive pipeline parallel. So the next thing I want to show is using distributed data parallel. And I have the very same script here, but making a few changes. So the first thing is that whereas in the previous script, when I loaded the model, I passed in device map of auto, and this automatically dispatches the layers of the model to the available devices, which in this case would be the GPUs. But in distributed data parallel, we need to specifically pass off the layers according to this type of format here. And we need to use a device string and pass that device string, which depends on which process, in other words, which GPU it is. And that will be passed into the device map. So it's a little bit of a more involved setup for the device map, which is then passed into the model loading right here. So that's the very first thing. And other than that, all of my training code is pretty much the exact same with one exception. When I use gradient checkpointing, so gradient checkpointing is a way to reduce the VRAM you need to store the activations on the forward pass. So when you forward pass, you calculate all of the activations, and those are used on the backward pass for calculating gradients. But of course, the longer your input sequences and the higher your batch size, the more activations you need to store in VRAM. So one way to reduce the VRAM requirements is not to actually store all the activations, but just store some checkpoints in the model. Now, if you only store the checkpoints, when you're doing the backpropagation, you need to recompute the missing activations and gradients effectively. So this is a way to reduce VRAM, but it means you need to recompute, so it increases the number of calculations for the training. But generally that can be a trade-off worth taking because it reduces VRAM requirements, so you turn on gradient checkpointing. Now, within gradient checkpointing, you need to set, when you're doing DDP or when you're doing fully sharded data parallel, you need to set some arguments. And the particular one to set is use reentrant. Use reentrant means that you use a more sophisticated way of recomputing within the graph of the gradients. So when you're filling in those gaps, you're using a graph that's going to allow you to more efficiently fill in the gaps, essentially. That's what use reentrant is doing. And so it's a more complicated approach, but it's a faster, more efficient approach. So if you want more robustness and you want your code to run easier, you'll turn this off because it's an extra complication. But if you want optimization, you'll turn it on. Now with DDP, it actually has to be false. It has to be turned off. And so I've got that turned off. So other than that, everything else is all going to be the same, with the one exception of how I run this script. So instead of running it with Python test ddp.py, I'm going to run it using accelerate, which is one of the packages I installed. So here, I'm going to run accelerate launch and then the script itself here. And this is going to boot up the script in a DDP type of approach. And you'll see right here, the number of processes is being set to 4. So it's auto detecting that I have one GPU, and that's correct. So it's all proceeding, and you can see the training is underway, and the training here has been completed. So that's how you run distributed data parallel. The key things to note are first, how you run it with accelerate launch, and also you need to make sure the device map is properly set. And last of all, you need to make sure, I think, especially if you're running on multiple GPUs, to use reentrance false. Which brings us to the next script, which is fully sharded data parallel. Again, everything is the same in this script. I've set the device map to fully sharded data parallel, but notice that in fully sharded data parallel, I actually don't need to pass in the device map. This is going to be handled by accelerate when I use it. So I have made that change. You'll see device map is not being passed in anymore to the model. Now scrolling down here, everything else is the same, except I am turning use reentrant on to true. This, as I said earlier, is more efficient. It significantly saves on VRAM. In fact, if you set this to false for fully sharded data parallel, it will result in a lot more VRAM being required, and you can go out of memory pretty easily. So I recommend setting this to true here if you're using fully sharded data parallel. Now there's one other update that needs to be made, and that's with respect to the LoRa layers. So when you run fully sharded data parallel, it takes the model and it splits it into modules. It doesn't exactly do it this way, but you can think of it like splitting up each layer into its own module. And then there is some code that will shard that layer. So it will set up the sharding to go across multiple GPUs. Now, because we are only using LoRa, we're not actually training the full model. So we don't need to shard the main model layers. At least we don't need to have any optimiser or gradients that are going to be updated for that. So we need a way to tell the fully sharded data parallel that when it's going to be setting up the wrappers, we want to have wrappers specifically for the modules that we're going to be training, because they need to have their optimizers and gradients wrapped. So there's a little piece of code here that's going to manage that wrapping specifically for the modules that we have set to training. And this little piece of code, you can add it in after the trainer has been instantiated, and it's then going to check if there's a fully sharded data parallel plugin. So if we've set up FSDP, which we will in a second with accelerate config, then it's necessary to basically import the plugin. and then import an auto wrap policy that has specifically been designed for PEFT. So basically there's been a little piece of code that's been written in the PEFT library that supports fully sharded data parallel for LoRa fine tuning. And we can import that wrapping policy and apply it then to the model, which will automatically wrap the modules correctly, given that we're doing LoRa. Okay, now, before we run this script, which we're going to run using accelerate launch, we actually need to run a configurator. And we run the configurator by running accelerate config. And this is the same configurator that can be run if you want to run in DeepSpeed as well. So let's go through a series of questions. Do we want to run on this machine? And by the way, this is the machine I'm SSH'd into, which is the Runpod machine. So yes, multi-GPU. So I'm selecting multi-GPU. How many different machines will you use? This actually refers to nodes, not really to GPUs. In fact, not to GPUs. So I'm going to press enter, which will just select one. I'm just running one machine from their standpoint. Should the operations be checked for errors? I'll default to no. Will I optimize with Torch Dynamo? Default to no. Do I want to use DeepSpeed? Default to no. Do I want to use fully sharded data parallel? Yes. Now, how do I want to shard? I want to do full shards. So these options here are roughly corresponding to the DeepSpeed stages 1, 2, and 3, where you can shard either the model parameters, the optimizer, the gradients, or just a selection of those. But we want to shard everything, so full shard. Do I want to offload to a CPU? No, because that will slow things down. What kind of wrapping do I want to use? So when fully sharded data parallel creates units that are then going to be sharded, how am I going to do that? I'm going to select transformer-based wrap. So it'll use standard wrapping for a transformer. Do I want to use the model's no split modules? So this will prevent modules from being split. A module, for example, being the K or the O modules within, say, the linear or attention layers. So I'm going to go with yes, which is not the default. I'm going to have no splitting of modules. What's the backward prefetch policy? I'm going to go with backward pre, the first option there. And for the state dictionary, so what is the state? Are we going to store it fully on each of the GPUs? And no, I'm going to shard it because that's going to reduce VRAM. And do you want to enable FSDP's forward prefetch policy? I'm going to default to no on this. Do you want to enable use original parameters? I don't want to use the original wrapping of the full model because I just want to focus on LoRa. So I'm actually going to decline this because I've got custom code. Do I want to enable efficient CPU, RAM efficient model loading? Yes, please. And then how many GPUs to use for training? I'm going to select 4 because that's how many I have. And lastly, my data type, I'm going to use BrainFloat 16 because my GPUs support BrainFloat 16 because they're the Ampere architecture. And now I'm ready to run with accelerate launch. So I'm just going to copy that little snippet down here. And this is going to launch my script using accelerate, using fully sharded data parallel. And you can see the model's already downloaded because we've run it already. And you can see here the trainable parameters. Notice that 7% of them are trainable. This is quite high because it's a small model. So the norm and embed layers are actually a relatively high percentage of the total parameters. So that's been loaded and we've run one step of the training and everything is being logged automatically to a new run in weights and biases. And so just to recap here on the fully sharded data parallel, the main changes are around the wrapping. I have to wrap the modules with this custom code because it's the LoRa modules that need particular attention. Also the trainable modules, the embeddings and norms that I've set to trainable. So that shows you a quick demonstration of the changes that need to be made to the scripts if you want to run in DDP or in fully sharded data parallel. Now, these are just test snippets. There's also a more complete training solution, and I want to show you one important change here too for fully sharded data parallel. This is a full Python script that can be configured to run with supervised fine-tuning or with ORPO, which is preference-based optimization. I have another video on that if you want to understand how that combines both supervised fine-tuning and techniques like DPO. This script here allows you to run with LoRa or without LoRa, and it allows you to run in DDP or with fully sharded data parallel. Now, there's one important thing to note. If you are running with fully sharded data parallel, when you get to the end of your training, you often want to save the model. And before you can save the model, you actually need to have all of the state on one GPU. So you need to move the state dictionary to just be on one GPU. And that's why I have this code here that checks if fully sharded data parallel is enabled, then it's going to set for the trainer accelerator state, and for the fully sharded data parallel plugin, it's going to basically set that to full state dictionary. And we need to have that set so that we're able to save after the end of training. If you don't do that, well, the state dictionary will be sharded across different shards and it won't be possible to save the model. But if you do it, the model will just be saved in one place. And I don't have a model saved because the test scripts here don't involve any saving. They're just literally running the training. But what we can do now is run through once this full training script, and it's set up by means of a configuration file, which you can go to right here. It's a YAML configuration file. So let's run fully sharded data parallel on this tiny llama model here. We're going to use the tokenizer associated with the model, but let's just say we're going to fine tune it to match the Mistral type chat format. So I've set a chat template there. We won't use 4-bit. We will use flash attention. We'll use bfloat16. This here is only relevant for running testing if you want to generate completions on prompts. The dataset we'll use is a DPO mix. For the training portion, we'll use Argilla DPO mix. And this can be used for doing ORPO, although I'll just show standard SFT here. For doing standard SFT training, we're going to use the chosen column, which is the best response within that dataset. And I've set my dataset training length here, rather the number of rows. So it'll just be a training for 1,024 rows. And then for validation, I'm going to use 128 rows, and I'm going to use the test split of that dataset. For configuring LoRa, I'm going to turn it on, set the modules and the other trainable modules as well, the LoRa OR and the LoRa Alpha. And then for training, I can set my batch size, gradient accumulation, etc. And I'm going to make sure gradient checkpointing is on and use reentrant. Actually, I'm going to set this to on so that I reduce the requirements that I have for VRAM. Now, optionally, I could run ORPO here by setting chosen and rejected columns. That's if I want to have a preference type of fine tuning. So everything is set here. If I don't set a new model name, it'll just default to the model base name plus a tag for the fine tuning. And I've also set my organization name for pushing later on using the push to hub script. So with all of this set here, I can just run the command python train .py. But actually, because I'm doing fully sharded data parallel, what I need to do is run accelerate launch train.py. This should kick off the process. There's one change I want to make here, which is to just set the max number of rows, because I don't want to wait too long for this all to complete. So let's just run with one step here. This should be commented out if you're going to do a full training. So it looks like the training is still going, so I'll interrupt. So I'm ready now to train, and I'm going to train with accelerate launch train.py. And this should kick off the script and get us training for one step of supervised fine tuning, because I have not turned on ORPO fine tuning. And once it's complete, it's going to save a copy of the model after having set up the full state dictionary. So here we're just going to see one training step. And if you want to look at the GPUs here, we can see what's happening. And you can see that the shards are loaded across all of the GPUs. My batch size is small, so I could increase my batch size a lot more. And all of the GPUs are being utilized here. So the training has been completed. And you can see my model has been saved. So the model is saved here within the Trellis Tiny Llama folder with a slug added on here for the specific type of training I've done. And here is the standard way to save the adapter model. Of course, that adapter model could then be loaded and merged. There is actually a script for running that. It's just push to hub, which allows models to be merged and then pushed up to hub. And there's also a test script that allows models to be loaded and to run inference on a set of prompts. The set of prompts can come from a data set that are specified here under test data set. So you can set up what data set is to be used just for generating test completions for manual inspection. Or there's also an option to just specify some messages. For example, here I've specified a few test questions that are possible to run. And once they've been run, they'll provide some output in the results folder. Just for example, I can run that with Python test.py. And actually, let's see, that's going to test just the base model here of Tiny Llama. So you can see it's starting it with a Tiny Llama model, that tokenizer, no 4-bit quantization. It's going to use this chat template, which actually will result in bad results because this is a base model that hasn't been fine-tuned yet. And here we have the output. So actually you can see some of the older results here. We've got the prompt, the correct response, and the generated response. Prompt correct and generated response here, which is not particularly good. This hasn't been fine-tuned. But you can see another model here I ran earlier, which is Quen 14B, and here the generated response is reasonable, and the same for the generated response here from Quen 14B. So that's just a demo of how this config file can be used in combination with the train.py and test.py scripts, and it can be used to run fully sharded parallel, data parallel, or it can be set to auto just to run a naive model parallel type approach. That is it for this monster video on multi-GPU training. And I'll just say it takes quite a lot of patience if you're going to try FSDP or DDP. The more GPUs, the more problems in general. So if you can, try and fit your model onto fewer GPUs, ideally one GPU. In the meantime, let me know any questions on DDP or FSDP below in the comments, and you can find all the materials linked in the description or over on trellis.com/advanced-fine-tuning. Cheers.